All right, so we're trying to do the following here. Indicate. Yeah. What we want to show is that this is not too far away. That's the degree distribution for the preferential attachment gamma. So after T arrivals, the probability. So with this definition PKT, which is that I'm just counting the total number of nodes who have degree A by time T. And you know, so this is a mysterious object for the moment. It's not clear why is this even coming up. But hopefully the mystery will be clear at the end of the questions. It's actually a solution to a recursive equation. That is where this is going to. So what we'll show is that this somehow is related to its expectation. That expectation has a recurrence relation whose solution is this. That's what it will turn out to. Directly, it's not obvious to see why one has a relationship with the other. That's what it is. Okay, so the main theorem we want to prove is the following, but the ingredients is what we are trying to do today. Max over K capital PKT minus K C times square T. This probability this is the major result we want to show. But before that, we'll actually work with this and its expected value. That is in two steps. All right. Here, what we're trying to achieve. This is the main theorem we want to prove. We won't go directly here. We'll first worry about this object and its expectation and try to see the deviation from its expectation. So we'll rather control PKT minus the expected value of this. It's like PKT in a different form. That's what we'll essentially do. And then that expected value is what we want to show is close to PK. All right, so let's look at an object which is not than PKT, NKT, which is the number of nodes. Expression I will indicate that so this by definition T times capital PKT. This is the definition. So this number is what we're going to control. And we look at NKT and its expectation and what can we see. So the proposition we're going to prove. So for any delta greater than minus for any C greater than square root 8 probability NKT greater than C times decision property. No, proposition. Will prove. This is proposition number one more, and then we can combine that to prove the result of the previous problem. Today's class will mostly concentrate on proving this. So now, today we'll nicely use martingales. We haven't used martingales now, so this is one good exercise. Okay. So, clear what we're trying to do? So now think of, so time is 0, so time is progressive. 0, 1, 2. Now I've reached time t. That's where we are going to say something. Well, pick up any index n between 0 and t. At 0, it's an empty graph. So the graph, so preferential attachment 0 is the graph at time 0, which is an empty graph, and so on. Even preferential attachment. So making this approximately sequentially in time because I'm going to condition on all these guys. So PAN is nothing but the graph at time, which is a random object, because every time a new node comes in, where it gets attached is a random quantity. So now define Mn to be the expected number of nodes with degree k at time t, conditioned on PA. This is going to be my object of interest. What can you say by looking at this object? Does Mn have any interesting property? The definition clear? So what did I do? I'm just conditioning on the some time n, which is between 0 and t. I'm conditioning on that. Looking at time t, what is the number of nodes with degree k? So what is M0? Let's just get our hands dirty. What is M0? Nothing is given. Expected result. Then it is simply NKT. Similarly, that is MT. NKT. Simply NKT because it is written this. These two extremes. Full information versus no information. In between, what is happening? Yes, but does Mn look like any interesting object? Okay, why is it multiplication? It's true. That's smart. The first thing is to just check brutally. What else is? What is Mn plus 1? By definition is. And for checking the martingale, what I'm supposed to do? Expected value. Yeah. Given what? From M0 from Mn. Yeah. Given Mn. Right here. Given Mn. Okay. Will that work? Mn is a complicated object. So what is the right conditioning here? Yeah. Does it appeal better? Yes. What is this quantity? with respect to PAN is what I'm interested in. The sigma algebra of interest is PAN. That's what is defining entity. I don't really have to worry about the same then. Okay, now this is by definition. What is the property between PAN and PAN plus 1? As time progresses, what happens? One more edge. No, so all I need is that this is the subset of this superset. And for my tower property, I needed that. There should be a sub sigma. So essentially, what is it? This contains less information. That contains more information. So that's why tower it will just push through. That should be nothing but expected value of NK given NX, which by definition is that's why exactly the martingale sequence. Nothing, you just plug it out and use the tower property. That's all I need. The most important thing was that this is a sub sigma algebra. That's what we need. Okay, so now this is a martingale. If I wanted to use Azuma holding, what more do I need? Or can you just directly say something interesting about it, other than it being martingale? Is it bounded? Yeah, because of the very definition of how the graph is constructed. There are at most t vertices. So the maximum number of nodes with degree k can at most be t. So it's also bounded. With bounded, it is martingale. So now I want to apply Azuma update. What more do I need? I would like to control the successive returns. So what? Guess what that answer should look like. The rigorous proof is likely more complicated, but you should be able to guess what that number. What is m plus 1 minus m? Very most. All right. One.
NQT what is 60 degree?
Yes.
You add one edge.
What possible changes can happen?
You're changing the degree of two vertices.
That is correct.
And change by at most 2.
So that's what you have to show slightly more rigorous. Because of the conditioning, you have to show slightly more rigorous. But what we're saying is that in fact correct. That from one step to the next, what happens? A new vertex arrives. It either stays on its like connected to itself, in which case its own degree goes up by 2. But the number of nodes with degree 2 only changes by 1. So this case nothing happens in terms of 2. It only is at most 1. But in case when it attaches itself to somebody, somebody's degree might go up by 1. But NKT for certain value could go down. So if somebody had degree 1 already existing, and you went and attached itself, your degree went up to 2. So the number of nodes with degree 1 actually decreased by 1. So both can happen. So if you always know what is like, what should you even guess? Then you want to prove something that it actually works out. There's a different story, but at least you can guess what. So at most 2 things could we're really changing in NK. For any fixed K. It can't be more than 2. That's what we will. So what our intuition is suggesting is in raw terms, what is expected value in NK? Because the object is slightly more complicated, you know, slightly more careful. At the end, it will come down to this. But the proof will go slightly down about it. It's very important for you to guess that. Then we can possibly prove something. Okay. We'll use the mountain to show a proof of rather. M9 minus M1 minus M1. That's all. Almost sure. Okay, so what do we mean? Yes, the time. So write this as article P. It's just equal. Another way of writing this. This is nothing but summation of the indicators. That's all. With the conditioning. Writing it one more time. So what's the difficult object here? If I want to compare Mn and Mn minus 1, what do you think is my basic difficulty? Currently, they are not comparable. You see, the conditioning is over different graphs, PAN and PAN minus 1. So, can I find the commonality in the conditioning is the question. Then I can compare these two things. So, up to PAN minus 1, they're essentially the same. This just has some extra information sitting there. So, can I add something here so that the conditioning is roughly over similar? It won't be the same objects, but at least comparable objects. Then I can take the difference and say the same. So, what can you do to add something here without changing the equality? So, this happens in information theory all the time. You keep adding random variables to the conditioning and making sure that the mutual information expressions don't change. Something similar is going to happen here. I want to add something to this condition without changing the equality. Otherwise, it will go both directions. If I add something new and something extra here, it could either increase or decrease. You want to make sure it doesn't change. So, what is the only thing that we need to put something in? So what can be an independent thing which I can make it comparable? Can you make it slightly more formal? Because eventually I want to be able to compare this and this.
So we started about PAN minus 1 and H.
Right. Independently of this, what will you? So you have this one graph until time n minus 1. It's the same graph as until time n minus 1. Now the nth guy arrived, and that's what gave you PAN. If I do something independent of this, keeping these two the same. So PAN minus 1. Now, how do I implement this? You put a Now I randomly toss coins. So these two exactly match until time n minus 1. At this point, I do an independent realization of where to add. See, the model is that every time n, when you arrive, you either get associated to yourself or you get connected to exactly one person inside. If I do this coin tossing independently, fixing n minus 1, these two graphs are independent. Correct? So now can you use an idea to make these comparables? And the resulting graphs here and here have the same marginal distribution. There's no difference. If I forget about this, I only observe this for even at time. And I forget this and I observe this. You should not be able to distinguish between them. So only when jointly looked, they'll match exactly at these locations. But there's no joint condition here. All I have is marginal condition. So I want to replace this n minus 1 and add an independent copy and still say something. What did that say?
There is one edge that you can add to PAN minus 1 to get PAN. So you look at the probability that you use that edge. Okay. When PN is added, multiply the probability.
That is more complicated. Why don't you just look at degree distribution in this graph? Let's call this PAN and this prime. They're indistinguishable. On the marginally, they're indistinguishable. This is on a prime. What's going on? Can I replace this with a prime here? I can. And if I were to condition on this additional thing from here, which is independent of this, I should not see any difference. I can always say I equal to B phi prime P equal to P. Given P A n minus 1, why is this equal? If you see this, then you're done. So D prime is nothing but degree in this graph. So now can you tell me why is this equal to this? You see that, then it's straightforward.
Both the graphs are identical and independent, right?
No. See what are the? This is exactly the same. I'm not touched that.
Okay. You're only changing the degree.
This you should not have an objection. That this is the same as this because I can't distinguish.
Okay.
I'm saying you can remove this. Why? Because until time n minus 1, I've kept it exactly equal. So in fact, I can remove this and claim that this term has become di prime, while this term remains EA itself. But now I'm claiming I can add PAN itself here with equality. Why is this true? Are you with me until here? Why is this true? That is, with a prime it is identical, and by my construction, PA n minus is exactly equal to PA prime n minus. So this is clear. Now I'm adding this extra edge, essentially what else? I'm still claiming that this is equal. Why? So look at di prime and its connection to PAN. Does it depend on PAN minus PAN minus 1? What is the graph at time and PAN? If I subtract out the graph at PAN minus 1, does di prime depend on that?
It depends.
Why? It's a prime. So whatever happened in one step, which is defining PAN minus 1, everything in this graph P prime is independent of that. As long as I put in PAN minus 1. So adding the additional edge as you claim it, I would rather say PAN minus 1. All that information is independent of what is happening in the prime graph. As long as I keep putting in PAN minus 1. I can't do without the PAN minus, but I can add something because that is not changing anything. Is it clear? This is the crux of the question. Because from this point onwards, you'll be able to compare Mn minus 1 and M.
You can't write PA and prime, right? I mean, that would be different.
No, that's not different. That's not, that actually depends on that. Because D prime has information coming from PA prime. So that's why we went in 3 steps here. So from here, we went to, let me overload the notation for a minute. This was straightforward. This is equal to this pattern. Now I'm removing this because of the condition that both of them are identical. Now, given that D prime is a graph on the right hand side, PAN minus 1 on the left hand side, and they only match up to step n minus 1, while progress beyond it is independent, I can easily put in that extra edge for the remainder of the graph here without changing the equality. That's all I've done. So you should think of it as PAN minus 1 union PAN subtracting PAN minus 1 is what is written as this. That's why this is equal.
By this way, we can say that will be independent of PAN plus 1 and plus 2 anything like that.
I'm not going to define any multiplication. You will be careful. If you progress this way, yes.
Because only up to n minus 1,
They are identical. So anything beyond it
okay.
in these two graphs is progressing independently. But given this, you can't say if I drop the conditioning on PAN minus 1, there's still 2. That's not true. They have correlated information, but that is being conditioned already. So anything new that is independent across these graphs.
Okay.
Now I can compare. I want to write it. Right? So that's all the technical difficulty really is. What you guessed to begin with was right. But because the conditioning is different, you have to be careful in how things are. There is some mention of That's what you should. Now what can you do? You want to somehow show that this is atmospheric. Now at least the conditioning is over the same randomly. Now you can use all your edge logic to lives. Now thing to notice is DI from Markov chain. If I tell you DI of M, what does DI of T depend on?
DIT minus. Yeah.
No, so you want me one step and say, suppose I tell you DI of M. Do I need to tell you anything more in PA M?
So what are you asking?
So instead of PAN, if I just give you DI of M, can I just replace PAN by that? So it's equivalent means there is a Markov chain.
Sorry, I didn't.
So PA, what is PAN?
Yeah.
PAN is the graph
Right,
line.
and that time.
Graph, it would graph.
Yes.
But for DIT, if I were just tell you DIN,
At time and the degree of ith.
no, DIN, yeah, that's right. DIT equal to K means what?
It has k edges. The ith node at time t.
Right. So how is it evolving is the question. So if I were to tell you DI of N, do I still need to tell you PAN?
If we know about all the i's from 1 to like
You know, DIN for all.
all yes. Okay. Then PAN is given like. Okay.
You want to know degree of vertex I at time t, you need to know degrees of all vertices at time n.
Give you a concrete example. You fix the I symbol. So how does it matter what somebody else has? I'm not asking you total number of vertices. What is DIT? For the ith node, what is the degree?
Yes.
So if I tell you some previous time what the degree was, that point onward, it doesn't matter how I arrived there. How does the graph evolve? There's no deletion, right? So fix a vertex I, and I tell you at certain time n, this is my degree. That time onwards, how does the increment happen? It doesn't depend on what PAN was. It doesn't really matter what all people were connected to. It's only depending on the next ones. And fixing given the information I have at it.
Yes.
So what you're asking for is something else that I need to look at the full graph. Here I'm fixing a particular one. The entity can be written many different ways. You written it in a particular form so that we can exploit all the properties. So instead of PAN, you can actually make it only DIN. Right? And this is the difference. Now all you want to bound is the difference. So when is it equal? Like each term by term, when are they equal?
Up to n minus 1.
No. So now we replace PAN by its counterpart DIN.
Okay.
Right? Now can you tell me where are these two terms non-zero? So if din is the same as di prime n, what's happening to this difference?
Is zero.
They're identical. Is this clear? Because up to n minus 1 anyway we condition that they're equal. It's only at given time n also they happen to be equal. Then the whole progression is the same, identical. So both probabilities better be the same. There's no reason for it to be any different. Okay, so now using this observation, what can we say? Well, how large is the difference? I'll write down everything on the board. I just want you to make sure that you see it through first and then I do it. So first think of PN being replaced by DIN. Up to n minus 1 anyway, these two graphs are the same. So the DI prime has the same evolution compared to DI. There's no difference. It's only going beyond is the question. So if at n also they happen to be equal, this is identical. These two terms are essentially identical because the progression is the same. So what is now? How can we count the difference? The difference will be at most how much? This is probability minus probability. So how can we, how large can be the difference?
1.
Okay.
T minus n plus 1 times 1.
So that would not suffice us. We want all of this to be at most 2.
Can you please repeat again why, means how we can change PAN into DIN?
Yeah, so how is DI evolving? DIS is degree of IR mode at time S. How is it evolving? So suppose I give you DI of S minus 1. What extra information do I need to give? Do I need to give you PA of S minus 1? So if I condition DI of n for any n up to t, I will just drop PA. I don't need that extra. Yes. And if I also add in addition that di of n is equal to di prime of n, then these two graphs evolve the same way. So the conditioning is fixed at time n. Yes. So then better be 0. So all that we have to worry about is when is di of n not equal to di prime of n. Given that everything else below before is the same. So how large can it be? It's being summed from I equal to 1 to t. But what is going on?
Up to n minus 1, we already know that both are identical.
Okay.
But after that,
Difference between T and D prime by T can be at first T minus.
Won't suffice about the
What is the difference between DIT and DIT prime?
Let's see source.
Yeah, but can switch one with another end.
Okay.
It is a kind of symmetric.
Yeah, so what do you want to say?
It can also be negative.
Let's say negative. That's true. Could you get some idea to begin with, where you guess something?
What I had said was going from t to t plus 1, the number of vertices in degree k changes by almost.
Okay.
Is fixed here.
Because Mn and Mn minus 1 are similar objects. This is written in a more complicated form. So what is your guess for this summation?
I will intuitively see what is about this difference. Probabilities.
But you have a nice intuition about Mn and Mn minus. Where did we lose our mind?
There are difference in number of vertices with different probabilities.
Yeah, but they're equal. So take an example and see what. And what is the sum over? Sum is over vertices.
Vertices.
Sum is not over time. That also happens to it.
So DIT and DIT prime can be different at most two vertices. I don't know.
See, DIT is for a fixed vertex at time t. It's not over time. So the summation is not over time. Okay. This one is good. Now, when can this be different? Fix an eye. When can this probability be different? If di of n is different than di prime. Okay. After when it is not equal. Whenever these are not equal. Okay, now what do this? Recursion.
DIN is not equal to DI finally. One of them got damaged.
As a whole, the total number of the same. That's what you have to see it carefully. When I'm summing across these vertices, एक का बड़ा दूसरे का घटा. So essentially, you just have to worry about one step, and that's sufficient. That's what I'm saying. Don't add across time, add across vertices. These are vertices. So this sum is no more than summation over I going from 1 through t indicator di. That's all. That be equal. This is okay. It's just capturing indicator. And when this happens, the difference is at most 1. That's why they indicate. Otherwise, it's 0. Now, this is at most 2 is what you have to see. Because this summation is over, vertice is not over time. So, this I really need to convince yourself. You reached over? Okay. What is this? Yeah, okay with this? Yes. What this is just restatement. Okay. That this is equal as long as these are equal. So this is not equal when they are not equal. Okay. So every time they are not equal, I'm counting at most 1. Okay. Yes. Then if you sum it over all of them, somebody is increasing, somebody is decreasing. The end result across these figures, it is only going to be amortized. A trivial probability times this, but that's too much. Don't want that. And anyway, your guess was on this expression, if you remember. What is happening really in one step? You just where this is coming from, it's exactly the same argument. That if you sum across t vertices, you're not going to get t times on this. This you just have to go back and just visualize. Take whatever example you want. Because if this is changing, something else is also changing somewhere else. So we increase somewhere, decrease somewhere. Because the total number of vertices is just t. Do not keep this final thing. Okay, now we are good to apply for the topic. Okay. For that, let's recall what we want to do this. Let ML be a martingale. Is good. And mu accepted by and then probably that when deviates from its mean, which is mu greater than a is less than equal to 2 times minus a square. This is the most interesting term, summation of 2 times whatever difference you produce here, that difference comes in 600. So larger the difference, weaker is the name. For our case, we produce 2. So that's the constant. Okay. And what was my mean mu? I don't have to count. Like all I'm interested in is NKT minus expected value. In this slide. So using that, I want to control max. Max is the only interesting thing. Max old. Okay, so for what values of k I can, this is vacuous. K greater than t doesn't make any sense, right? Nobody can have a degree greater than t. So essentially, this is vacuous. So that's why taking a union bound, I can just move k here, k going from what is t plus the worst case t plus 1. T also should work. That much of probability that. Now I can apply this with a summation outside, but the exponential will take care of that. How much can I say here? With C square root T log T. So A will get replaced by C times square root T log T. And KIs are just simply 2. Yes. Okay, so how much I'll get?
Minus C square T log T by 2, 8 and 8.
Right, so what will I get in the power? Minus E minus C square. Eight. That is why I want C to be greater than square root 8. T and T cancels. Log T will not be sufficient to kill. So that's why I want C to be slightly larger than square root. So as long as summation.
Why do we want to see less than 2 or
No, but what about the summation? Supposed to be summation.
e raised to minus log t is e raised to log t and it is t.
That's correct. Minus t, right?
Okay.
Or 1 by t. So you get 1 by t, but
1 by t raised to c squared by 8.
yeah, that is okay. But I'm worried about the summation. What did I want to prove? With the t plus 1 outside, right? And each of them is just going down as little over 1 by t. That is okay. What do I want to prove? Okay. So all I want to prove is little over 1. I want to prove little over 1 by t. This will give you little over 1 by t. When I'm summing it over, k goes from minus to t plus 1, I get little over 1. That's what I want. Okay. So that's the first part of the problem, which is now done. That NKT and the expected value are not too far away. Now what we want to show is that the expected value of NKT and PKT are not too far. If you can do both, then this NKT, then we can say that NKT is close to little pk, NK is not a representative of capital P. Okay. Now that is slightly messy. Let's what we want. Use to and PK is some weird expression. That's why there's no real intuition like why it would go to PK. So instead, what we'll try to do, we'll try to write a recursion for this. And in a weird roundabout way, argue that suppose PK was in fact close to this, then PK should satisfy. PK should have a solution. And that solution is what the recursion equation does. So let's concentrate on the recursion for this. So can you think of a recursion for summation MKT, expected value of MK? Sorry? T plus 1. You fix a k, so that's what we did. This is nothing but a limit as t goes to infinity. K is fixed. So one step, nothing much really should happen, but so going from t to t plus 1. How does the expected value of NKT?
We add an edge to degree k vertex increases, we add an edge to degree k minus 1 vertex.
So there are 4 possible events. So at time t plus 1, a new vertex arrives. Because of its arrival, 4 possible events can happen which can change nk of t. Can you list all of them?
It attaches to a degree k vertex, attaches to degree k minus 1.
So let's say event number 1, b of t plus 1 is arrived. So there was this graph sitting down there, and let's say it attaches to u. Now, depending on you, what all possibilities are there for nk of t? See, nk of t is counting the number of nodes with degree k. That's the difference between what we wrote there. The expected value di of t, just specific to a particular node. This no longer works here. So it's much easier to handle nkt directly. So suppose it's going to attach itself. See, the possibility is it attaches or doesn't attach. So that itself is a two class. So let's worry about first it goes and attaches itself to somebody. So what is the change in nkt because of it attaching it to somebody? Okay. Give me precisely what happens. So given that, so event one was you had degree k minus 1. That's one possibility. In which case, what happens? It goes up by 1. But what is the probability with which I am going to pick this guy?
One by t.
No, differential attachment.
It will be k minus 1 by t.
See, how many nodes are there with degree k minus 1 at that time?
K, nk minus.
And among them is uniformly random. See, from the outside, it's a very difficult model. But once you know that I'm going to go and attach to k minus 1, all the information I've given you is that among all the nodes which are degree k minus 1, I'm picking one uniformly random. So that simplifies it. 1 by. So you had degree k minus 1, nkt plus 1 equal to nk plus 1 probability 1 by nk minus 1t. Correct?
Condition to the fact that it attaches to the zero.
No, so this exactly this with this is going to happen with this probability. What else can happen in this setting where it's actually going to attach something? So 2 is you had degree k itself. Then what happens? Then nk t plus 1 is in fact 1 minus. Because you push that guy's degree up, so the number of nodes with degree k actually went down. And this happens with probability 1 by nk. What else happens? It doesn't attach anybody. No, there's something more. For k equal to 1 and k equal to 2, you have to 0. That's it. So when a new node arrives, it gets attached to somebody. Its own degree also goes up by 1. So you are producing a vertex with degree 1. So if k was 1, I also have to account for that. If it doesn't make a self loop with itself.
Yes.
But that only is k equal to 1 and k equal to 2. K equal to 2, if I make a self loop for myself, that's k equal to 2. Otherwise, it's always outside. So how do I like that? You can put an indicator k equal to 1 and tell me what happens. See, both these are true in case 1. Because it's attaching itself to somebody. So what is my probability of attaching it to somebody? This is always a bimodal, right? I make a self proof with myself a certain probability. 1 minus of that I actually go and attach to somebody else. So all of this is happening with that probability. So when k is 1, you also have to increment this by 1 more. That's all you have to do. Otherwise, I don't care. So it's only when I'm counting for k equal to 1, I have to worry about what is the degree of this newly arrived node. Is it making a self loop was connecting somebody. So when it's connecting somebody, for k equal to 1, I have to increase this. For k greater than 1, I don't know. This is all there is. Not clear.
But if k equal to 1, then you cannot have any vertex in with degree 0, right?
Right? So I don't know what you call here, only for the new. That's right. And k equal to 2, it does happen because there could be no with degree 2 here. And if I make a self loop, I just increase it by 1. So these are all possible polygons. This takes care of the rest of the graph. And then there are possibilities of this becoming a k equal to 1 degree naught. And k equal to 2 degree naught. So the way we have defined the model, there is a probability with which I don't attach to anybody. Everything else, 1 minus of that is this probability. And avoiding writing that long expression. But remember that. There's some probability to this, like a self loop. And the rest of the probability attached to somebody. So all these guys are under that. It's only one such thing with which I just isolate myself and the process is simpler. So if you write it down, you get the long form. So it's going to be that you are writing the difference. Here, t plus 1. And p d1. So these are all of this probabilities with which certain events are happening. That was the plus 1, this is the minus 1. Okay, plus 12. Becomes the indicator k equal to 1. 1 minus the probability that I attach to myself. To get the nuisance right. And plus k equal to 2. Is this probability. So whatever we did on the last board, it's just written in long form. Okay, now how does it help me to write the recursion? What I really want is expected value of nk of t plus 1 expected value of nkt and nkt minus 1. Unavoidable t minus 1. These guys, the k minus 1 is unavoidable. You have to. So it could go down, it could go up.
We have this recursion, right?
Yes, but that's not a nice form. I wanted an recursion with respect to expected value of nk of t plus 1. What can this is everything is there on the board. You just have to stare. Simplest thing would be to take an expectation of this to get rid of all the conditions. So if I take an expectation here, you take an expectation there. All I will remain is this indicator k equal to. Because if this is not a probabilistic event, this is just which k I'm looking at. If I'm looking at k equal to 1, I have to take care of this. I'm looking at k equal to 1. So just taking expectation and be there, and then getting it value of nk t plus 1. We're going to move the minus over there. Expected value of nkt plus let's call this w1. Expected value. I can add this 1 plus w. Call it w1. So this should be minus. All right. this times this plus this. Writing all these terms as W1. Oh, now what? Remember, what did I want? I wanted to write a recursion for NK. That much I have accomplished so far. But if I wanted this to be close to, I don't know the value of pk. So if I suppose I want this to be equal to pk times t. Remember the definition, nk is t times the correct quantity we're looking at. So what was
Those things will look out probabilities, right?
which ones?
The right hand side indicator.
Indicators are not random variables.
Okay.
Indicators are only counting for the value of k, which k I am interested in. That's why there is an interest. So remember the capital PKT, this t times, no, sorry, it was 1 by t times. 1 by t times of NK by definition. So you remove it here, and I want this to be close to little pk. So this should be better to be close to little pk. If such a pkt exists, is it clear what I'm trying to do?
Can you please repeat it?
What is NKT? Expected value of, not expected, number of BIP equal to k. And this was 1 by t of this. What do I have embarked upon? I tried to show that this is close to its expectation. Now, if I want this to be close to little pkt, what should be the expectation close to? This itself. This I want to be close to little pk.
Yes.
What do I want NKT to be close to? Expected value to be close to little pkt. If this is going to be a solution of this equation, what does pk look like in this? Can you just stare at it and tell me? And also use the fact that t is going to infinity. What really you should exploit? So this is not a formal way, but this is how to build actually intuition understand why this strange looking expression, which is by our definition pk, is actually close to this expected value. So think for a moment why this should be. If for each t this is true, what can you approximate the difference between time t plus 1 and time t of the expected value of nk?
W1 minus W2 times expected value of NK minus.
No, in terms of pk. So supposing that my answer of the expected value of time nk of t is close to pkt, what do you expect to happen?
Difference would be PK.
What? Like pk into t plus 1 minus pk into t. So you get pk. Perfect. So now put that difference in this equation as equal to pk.
PK is W1 minus W2 times.
So W1 into the quantity of interest, which again multiply say pk.
PK minus 1.
Right. So what am I trying to get? I'm getting pk equal to W1 times pk minus 1 times t
Minus
and plus some extra terms which are not really under my control. Pronouns is clear also.
No, I'm confused with what he answered.
So what are we trying to show? Trying to show that the expected value of NKT is equals to PKT. This has to happen. We don't even know what the answer is, but if this has to happen, what has to happen to this equation? So if I subtract expected value of NK of T plus 1 minus expected value of NKT alone. Okay. What do you expect that difference to look like? Just PK.
Why? NKT plus 1 and NKT, difference of their expectation.
Yes. If each one is PK into T,
Okay.
first of all, give me PK into T plus 1.
Yes.
Second, give me PKT, the difference is PK.
Yes.
So I can somehow write that difference in terms of PK alone. Now look at the term multiplying W1. Okay, that is in terms of K minus.
Actually, I am not able to keep the terms in my mind.
You can see W1. W1 is on the board. What is the term multiplying W1?
NK minus 1.
Okay, so if my conjecture was true, that it is in fact PKT, what can you write this as?
PK minus 1 times
T. Right. And the rest of the terms, there is no dependence on PKs.
yes.
So, what does the recursion look like in this approximate form? Take delta equal to 0, T large. If you want to. So what happens to these terms when multiplying the indicators? Only the indicator K equal to 1 survives, indicator K equal to 4 disappears. So delta 0 and T large. This is going to 0, this is going to 1. So this will get just nice enough terms. What going to happen to this?
PK minus 1 times P2.
But there is something dividing. W1 also has a T dividing.
Okay.
So that will go washed away. Something similar going to happen to this.
Okay.
So as long as you take T large, actually beautifully comes up.
Okay. Limit.
Not even limit, just T large.
Okay.
So none of this is watertight, but this is exactly what the rest of the group is very ugly. You won't get anything out of it. And why that funny looking expression is the right answer. So from the previous equation, before we have been NKT to be equal to EK times T. We get PK or P large, where W1 goes to 1, W1 goes to 0, W2 0. No, both of them are going to 1. You get PK equal to K minus 1. It's written as it is. So you don't have to make any. T will cancel out here. That's the interesting part. Because this guy has a PK minus 1 times T. So T will disappear from this sample. We'll just we'll drop this guy, give the 2 plus better. Right. Just the 2 plus PK minus 1. And this minus relation term. PK plus indicator. This is what you get if you were to surmise or make an assumption that this is what I really want. Now look at this expression. Drop delta. What does it look like? Then move this guy here. So So it is pk plus k minus delta over is equal to so now is equal to so for the moment you can throw away the case k equals 1. What does it look like? Pk is nothing but a multiplying factor of pk. This is easy to solve. If you have a recursion of this type, that's easy to solve. That's precisely the answer. So pk is nothing but this weird answer which you are expecting. Gamma of q plus 1 times gamma of 3 plus 2 delta. This is really the bottom line. That how you actually arrive at such an ugly answer is because of this recursion. And this recursion is not very unnatural, actually very natural relation. So you want me to remind what did we really do? This was the punchline. The difference between time t and time step t plus 1. Then we just take the expectation on one side, so you get an equation of this type. At this place, we made the approximation. But supposing that this is actually true, what pk can I expect? That is the pk I can expect. There's little more work needed to make this prototype. But punchline is this. This is what you should take out. That if I were solving such a problem, what would I do? This is what I would. And this is a very powerful technique. In many different models you will see, trying to see one step in expectation what will happen. And sometimes, once you write this equation, you're also able to write a differential equation. So you could divide this nkt plus 1 by minus nkt divided by time essentially. Then in 1 unit step at time t, what is happening? Some nice relationship holds here. There's a big machinery to say that the difference equation, which is on the left hand side, and the corresponding differential equation, they're not two different. So there's something called Curd theorem. Which connects the trajectory of these two in the discrete time versus the continuous time. And in the continuous time, it's very easy to find answers which you can portrait back. So that's also a big machinery you will use. So I'll see it next time if I in the mode to prove this rigorously or I'll move to something else. But punchline is already there. That how we are actually controlling this is using these two steps. The proposition we proved today showed that NK is close to the expectation. The next step is to show that the expectation is close to the pk. The following proof is to get to that, but this is very important. But until here, everything is watertight. It's only this one step I'm making a leap and trying to see what insight we can get.
Supposing that both are equal, the expected would have.
No, these are equal. All I'm leaping is this.
Yes.
There is no other leap. Just like backward. Assuming and proving. So guess and prove in some sense. So that's not what it should be. All right, so let's stop here.